Okay, with this solid beam, we're going to have to break the mass up into little increments of mass, little infinitely small pieces of mass. Starting at one end, here's a little tiny piece of mass, and then the next one's another little piece of mass. But these would be infinitely small. Each one would be a dm, and this goes all the way on down the line, dot, 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 all the way to the other side. So if we looked at this little piece of mass, that little mass would be dm, and dm would have a length which would also be infinitely small from here to here, which would be dr. And from the axis to the dm, each dm has its own unique r value, which is different than dr. R is how far away dm is from the axis of rotation. Dr is the corresponding little change in length. So each little dm has its own contribution to the total moment of inertia. Little dm's contribution to the total moment of inertia is di, a little piece of the total moment of inertia. So di is equal to dm times the corresponding r value for dm squared. Now, if we want to find the total moment of inertia, we're going to have to add up all those little contributions. I equals the integral of all of the di's. And that would equal the integral of all of the dm times r squared. But usually it's written r squared times dm, and the parentheses are understood that you start with the integral sign and you end with the dm. So the formula for the moment of inertia when you have a continuous mass is the integral of r squared dm. But we don't like to integrate over the mass. We like to integrate over like x, like dx. And in this case, we're going to integrate over dr, which is kind of like a dx. So we need to transform dm into dr. So recall, linear mass density is equal to the mass of the beam divided by its length. If I rearrange that, mass is equal to lambda times length. So if I multiply the whole length times the linear mass density, that would give me the whole mass. But what if I just multiplied a little piece of the length times the linear mass density? Well, then I would only get a little piece of the mass. And another name for a little tiny piece of the length is dr. So dr times lambda equals dm. dm is a small little piece of the mass, infinitely small for that matter, and that's equal to lambda times a little piece of the length, which is along the radius, so we can think of that as a little piece of the radius, dr. So that's what I'm going to use to transform the integral. So now it becomes I equals the integral of r squared dm. But instead of dm, I'm going to write lambda dr. Now, my boundary conditions, I'm starting from this side of the beam, going all the way over to that side of the beam. And when you're in the center, r equals 0. When you're way down here, r would equal, half of the length. But I want to indicate how I'm going all the way across. And since it's r squared, I could say that over here, r is equal to negative L over 2. And then I'm going to do this all the way through to over here where r is equal to positive L over 2. So this here has a lower boundary condition of negative L over 2 and an upper boundary condition of positive L over 2. And now I'm ready to integrate. So I equals, I could pull the constant out front, lambda times the integral from negative L over 2 to positive L over 2 of r squared dr. Now, remember, what we initially set off to do was to take the sum, the integral, of these products right here. But rather than take the sum of these products, what we could do instead is use the fundamental theorem of calculus, which says that that sum can be found by taking the antiderivative of the function that's sandwiched in between the integral sign and the dr. The antiderivative of this little piece right here. So I equals lambda times the antiderivative of r squared. Well, I have to raise the square by 1 power, so that becomes r cubed. But then I have to multiply by 1/3. And you could check that out, because if you took the derivative of that, you would get r squared. And then this goes from the boundary condition, negative L over 2 to positive L over 2. And the moment of inertia equals lambda times 1/3 times r cubed. Well, I'm going to put in this boundary here, positive L over 2, and that's going to get cubed, minus, I'm going to put in this here, so the 1/3 times negative L over 2 cubed. So I equals lambda times 1/3. L over 2 cubed is going to be L cubed over 2 times 2, 8. Minus 1/3. Now, negative L over 2 cubed, it's still going to come out negative, because if you have a negative times a negative times a negative, these two end up giving you a positive, and then you multiply by another negative, and you get a total of a negative. So this is going to end up being negative L cubed over 8. And when you subtract that negative, it ends up becoming like an addition problem. So this ends up equaling lambda times 1/3 L cubed over 8 plus 1/3 L cubed over 8 and let's go up here and get rid of that. So that's going to give us lambda times 2/3 L cubed over 8. What is that lambda right there? Lambda is the whole shebang mass divided by the whole shebang length. So that's mass divided by length times 2/3 L cubed over 8. So the moment of inertia ends up equaling one of these L's is going to cross out with one of those, leaving 2. And then this 2 is going to cross out that to a 4. And then 3 times 4 is 12. So we're going to be left with 1/12 mL squared. And that's the answer. The moment of inertia of a solid beam, mass m, length L, rotating about an axis through its center of mass is 1/12 mL squared. And of course that axis has to be perpendicular to the beam.